Hello, and welcome to Lecture 10. This week we are talking about fluid mechanics. We're going to add a few learning outcomes to this week's lecture, in that we are going to apply some fundamental principles of fluid mechanics to energy systems, and we're going to continue to work with Newton's laws of motion, make sure we're able to explain and use physics terminology as related to lab activities, and also demonstrate lab activities and define concepts and terms related to fluid mechanics. As we introduce physics definitions for fluids, liquids, and gases, principles and laws that will allow us to describe dynamic fluid interactions, our main goal will be to apply these concepts to fluid handling systems. Fluid is another one of those words that has a very specific meaning in physics. And again, it's slightly different than the way you might intuitively assume. For physics, the definition of fluid is any substance that can flow and conform to the shape of its container. Often, fluid is used synonymously with liquid, but that is not always the case, as liquid is another definition in physics. If we look at the containers below, the blue substance, as it fills the beaker, occupies the odd curves and shapes of the beaker, but the pink substance continues to maintain its own shape. It does not conform entirely to the shape of the beaker. Another way to think of the definition of a fluid is that fluids have no resistance to shear stress. If you were to push on the substance laterally, you would immediately deform the substance and create a new shape. When we think of a fluid, many of its interactions with other objects will depend on the amount of that fluid that is present in the space it occupies. This is the volume of the fluid. This characteristic is referred to as density. It's represented with the symbol rho, which is just a P without a shoulder, and it measures the amount of mass per unit volume. So our formula for density is that rho is equal to mass divided by volume. Our units for this characteristic are kilograms per meter cubed. There are other conventions like grams per centimeter cubed, but we will stick with the kms standard units. Let's look at an example for the density. Find the density of a gold brick if you know the mass is 19.3 kilograms and the volume that it occupies is 1 times 10 to the negative 3 cubic meters. So we grab our formula, rho is equal to m divided by v. We input our values that we know, 19.3 kilograms and 1.00 times 10 to the negative 3 meters cubed. This would give us 1.9 times 10 to the 3 kilograms meters cubed, or more appropriately formatted in scientific notation, 1.93 times 10 to the 4 kilograms meters cubed. An object with greater density will feel like it weighs more than a less dense object of the same size. That's because in that same volume, there's more material occupying the space. For reference, we know that water has a density of 1,000 kilograms per meter cubed, that's a metric ton per meter cubed, and another density value could be considered as 1 gram per milliliter. If we compare that to the gold brick we just calculated, gold is roughly 19 times as dense as water. We need to consider another concept that's similar to density, but this concept, pressure, allows us to determine how forces are transferred by fluids. We define pressure as the force per unit area. That means we calculate pressure, represented by the variable capital P, as the force divided by the area. This means it will have units of newtons per meter squared. In many of the applications that we work on, we'll consider the component of force that is perpendicular to the applied area. This means we only want the amount of force that's pushing into or out of the surface. This unit of newtons per meter squared is going to be referred to as a Pascal. So the units of pressure are pascals, and 1 newton per meter squared is equal to 1 Pascal. Again, we'll look at an example, this time for pressure. What is the pressure at the bottom of an aquarium that holds 1 cubic meter of water with a base area of 0.300 meters squared? So we'll grab our formula, pressure is equal to force divided by area. And our force applied here is the weight of all the water in the aquarium, so we'll replace force with mass times gravity. The amount of mass we have depends on the density of water, which we saw in the previous example, so we'll replace mass by rho times volume. And now we can start to input our values. We know the density of water is 1,000 kilograms per meter cubed. We know we have 1 cubic meter of water, and the weight will need to be calculated using the acceleration due to gravity. And we were told the area of the base is 0.300 meters squared. Calculating, this tells us that we would get approximately 30,000 pascals of pressure on the bottom of the aquarium. The way we talked about this example lets us see that the pressure in the fluid is caused by the weight of all the fluid above a position pushing down. Because the weight of the fluid is dependent on the density and the volume, we can see that the further down we go in an aquarium or a body of fluid, the more pressure we will experience. Measuring and calculating density is fairly straightforward. However, our atmosphere can make measuring pressure slightly difficult. When we think of pressure, we need to determine what pressure we want to measure. We can measure the gauge pressure, which is the pressure caused solely by the fluid we are interested in, and that's equal to the density multiplied by the gravity multiplied by the height of the fluid in our container. Or we could measure the absolute pressure, which includes all pressure acting on our fluid. So if we want to know all the pressure acting at the bottom of our aquarium, we would have to consider the force from the weight of the water pushing down, as well as the force from the weight of all the air above it also pushing down. Absolute pressure, P subscript ABS, is equal to the atmospheric pressure, P subscript ATM, added to the gauge pressure. We consider atmospheric pressure at sea level to be 101.3 kilopascals. You should note that this means a pascal is a metric unit and uses metric prefixes. The other thing to note is that atmospheric pressure can change based on the current weather conditions. Here, I want you to ask yourself, in the previous aquarium example, did we calculate the absolute or the gauge pressure? Now we shift our focus from definitions to principles. These principles will shape our understanding of fluid dynamics. The first principle we look at is Archimedes Principle. This principle defines the force that allows objects to float in a fluid. An object in fluid will experience a buoyant force equal to the weight of the displaced fluid. So if we consider a blue block of fluid and we drop an object, the purple block, into that fluid, the purple block displaces an amount of fluid. This means it has pushed that fluid out of the way. We know from Newton's third law that whatever force it uses to push things out of the way will have a reactionary force. This reactionary force is our buoyant force. And we found that we can calculate the buoyant force is equal to the mass of the displaced fluid multiplied by gravity. And again, we see that we can replace mass by the density of the displaced fluid and the volume or the amount of that fluid that's displaced. Let's look at a comparison of the net forces and consider the dynamics. If we have a buoyant force that is greater than the weight of the object, then the net force would be positive. So the object rises in the fluid. If we have a buoyant force that is less than the weight of the object, then the object will sink in the fluid. What about if we have a buoyant force that's equal to the weight of the object? Then the object is in equilibrium, which we also call neutral buoyancy. I want you to take a moment and consider what neutral buoyancy means. Do you know whether or not an object with neutral buoyancy is sinking, rising, or staying in the same spot? We can look at an example here. Consider an object with 852.6 newtons of weight that displaces 8.878 times 10 to the negative 2 meters cubed of water. Will this object sink or float? Well, asking if the object sinks or floats sounds like a dynamics problem. So let's look at the net forces on the object. There's a buoyant force and a weight. We can calculate the buoyant force using the formula above and add that to the weight. We can substitute our values, which is 1,000 kilograms per meter cubed as the density of water, the volume of water that's displaced, and multiply by gravity. And then we'll add to that a negative amount of the weight, again, because it's in the opposite direction of the buoyant force. And calculating, we see that we have a negative net force. This means that our object will sink. We need to take some time and clarify a misconception that's repeated in your textbook. We do this with a thought experiment. So we have an object on a string. Specifically, we have a worm and a hook on the end of a fishing line. The question asked in your textbook is, does the worm weigh more out of the water? And I want to emphasize how terrible this question is. Recall, weight is the force due to gravity. Being submerged in water will not decrease your weight. Let's look at what actually happens. Being submerged in water will reduce the net force that the worm and the hook apply to the fishing line. If we are out of the water, then the forces acting on the worm and the hook are the weight of the two objects combined and the force of tension from the fishing line. Once we submerge the worm and the hook in the water, then we start to experience a buoyant force. The weight will still be the same, but the buoyant force will now take away from the amount of tension required to hold the worm and hook from sinking. This will give you that apparent feeling of a smaller weight, and it means that when you try to move objects underneath water, you actually have to apply less force to lift them, but that does not mean they weigh any less. I think this is a good spot to include a think about this problem. With what we've seen about buoyant force, does the buoyant force change based on the depth? And this has the caveat if the two different depths you want to consider both have the entire object covered. The next principle we consider is Pascal's principle. This principle will allow us to understand how fluid transfers forces. The principle is that enclosed fluids transmit pressure unchanged and in all directions. This means that if we consider location 3 and location 4, the pressure in these two locations will be equal. This means if we substitute pressure for force divided by area, the force divided by the area at position 3 will be the same as at position 4, which is the same as at position 1 and at position 2. In practice, Pascal's principle allows us to gain mechanical advantage using hydraulic systems. This mechanical advantage presents itself in two ways, meaning there's an advantage and a consequence. The mechanical advantage is that we have a force multiplier. Using Pascal's principle, we can apply a smaller force on a smaller piston to be able to lift a larger force with a larger piston. Because the pressure at position 1 has to be equal to the pressure at position 2, then we know that the force over the area at position 1 is equal to the force over the area at position 2. We can rearrange this to find the unknown force in the diagram. So we'll see that the mass of object 2 multiplied by the acceleration due to gravity multiplied by the two areas dividing each other, and we'll cancel out that factor of pi. We see that if we apply a force of approximately 20 newtons on the smaller piston, we'll be able to lift the mass of the car, which actually has a weight much greater than 20 newtons. Well, we haven't spent much time talking about mechanical advantage. With all machines that provide a mechanical advantage, there has to be a trade-off. So we get more force, but we have to apply that force over more distance. So we have a displacement reduction. Let's add to our problem. If we want to lift the car 0.120 meters, how far must we push the smaller plunger? Even though we get a mechanical advantage, we can't break the conservation of energy. So this means that the change in energy at position 1 has to be equal and opposite to the change in energy at position 2, which means the work that we put into position 1 is the same amount of work that we get back at position 2. So this is force multiplied by change in position. We'll rearrange to find that change in position at plunger 1, and we'll substitute the mass of the car, the acceleration due to gravity, the distance we want to see the car move, and our force that we previously calculated with. And we see that to get the required height with the mechanical advantage we had, we would have to push our plunger for 75 meters. I will point out that this is a very exaggerated example. We mentioned earlier that while many people will use fluids and liquids, those two terms, interchangeably, they're not necessarily the exact same thing. A liquid is a special type of fluid. A liquid is a substance that will maintain its density. That statement has a couple of consequences. This means that liquids are incompressible fluids, which means you can't add pressure on them to shrink the volume. So that also means that liquids will keep a constant volume. This gives us an additional approach to apply to Pascal's principle. In our previous example, we could have used that the volume of our pistons had to remain constant, which means that the change in volume over at position 1 would have to be equal and opposite to the change in volume at position 2. And because our pistons are round cylinders, the volume is pi r squared h. And we can rearrange to see that the change in height at position 1 would have to be equal and opposite to the change of height at position 2 multiplied by the comparison of the two radii squared. And we see that we get the same distance that would have to be traveled. So we've seen how liquids transfer forces and how forces apply to liquids, but what about the forces in liquids? So we now consider the molecular forces acting on any liquid and its container. It's important to remember that all substances, fluids, liquids, solids, are made up of molecules, and there are forces that exist between these molecules. We have two terms that we're going to introduce: cohesion and adhesion. When considering cohesion forces, these are the intermolecular forces inside the liquid. So we see that we have some droplet of liquid here, and we have multiple molecules inside of it. And for each molecule, there'll be attractive forces acting on it from all surrounding molecules. You see, we have forces acting on it from all directions. These are trying to pull all the molecules close together. Adhesion forces are the forces present between a liquid and another surface, usually its container. So we'll see here that if we look at some container in purple, and again a droplet with its internal molecules, those molecules will have all of their cohesion forces acting on them, but also there'll be forces acting on the liquid molecules from the molecules in the container. As sketched here, we see that there's rather small attractive forces between these two molecules. When we think about cohesion forces, there's a consequence of the net force on the molecules at the surface. If we look at all the molecules around the surface, we know that there are molecules internal to them, so there's attractive forces pointing in, but there are also attractive forces between each molecule at the surface. These again are trying to pull all the molecules together. We call all of these attractive forces on the surface molecules surface tension. The net effect of all the surface tension forces is a net force inward that's perpendicular to the surface at all points, as well as a net force per unit length along any line on the surface. This net force per unit length along the surface is what we refer to as surface tension. Now there's many symbols that you may see used for surface tension. It could show up as sigma, capital T, or even gamma. But again, the units are newtons per unit length, or sometimes referred to as joules per meter squared. So the amount of energy a surface is able to contain within its area. We saw earlier that when a fluid interacts with a surface, there will be an interaction of the cohesive forces internal to the fluid and the adhesive forces between the fluid and the container. Comparing those two forces gives us a new method of classifying materials. We can have materials that we refer to as non-wettable and wettable surfaces. Non-wettable surfaces are surfaces where the adhesion forces are less than the cohesion forces. So if we consider a drop on a non-wettable surface, we see a rather large cohesion force internal to the drop compared to relatively small adhesion forces between the droplet and the surface. Comparing that to wettable surface, where the adhesion forces are greater than the cohesion forces, we see that relative to the adhesion forces, our black internal cohesive forces are relatively small. So the adhesive forces dominate the droplet and they actually pull it down closer to the surface. In either of these situations, non-wettable or wettable surfaces, the most readily available observation to make this distinction based on is the angle between the surface of a droplet and the surface it rests on. So we've drawn in the angle we're thinking of for the non-wettable surface. And we see that this angle has to be measured through the droplet. But if our forces of cohesion are greater than our forces of adhesion, then our angle will be greater than 90 degrees. Comparing that to a wettable surface, our force of cohesion is less than our force of adhesion. And in this case, our angle will be less than 90 degrees. Again, the angle is measured through the droplet. In surface interactions with tubes of wettable materials, we can observe an interesting interaction. The capilliarity is firstly responsible for the concave meniscus you observe in graduated cylinders. But that effect can be even more pronounced based on the radius of the cylinder. So the smaller the tube you use, the greater the meniscus effect or capilliarity is, raising the level of liquid in the tube. To understand this, let's zoom in on the interaction point or the meniscus of one of these liquids and consider the net forces. So if we look at our meniscus, we have molecules in the liquid, and the molecules at the edge of the tube will have an adhesive force towards the container, whereas the molecules in the middle of the tube will have a cohesive force between all of the molecules. All of the molecules will also have a weight based on the total amount of liquid being drawn up the tube. The net effect of all these forces is a slight net vertical force at the edges. Now, in wettable materials, this will be a net force up, which is what we'll continue to look at, but you should know that in non-wettable materials, like mercury, this would be a net force down, and you'd see the reverse direction of change for capilliarity. Let's shift our focus now and look at a top view. So we'll look at the top of our tube facing down, and we see why the smaller the tube, the more capilliarity we get. So if we consider the molecules around the edge, we know that there's a slight vertical force pulling those molecules up compared to the molecules in the middle, where there's a slight net force pulling them back down. And this is due to the weight being applied to the internal molecules, but not a force of adhesion. In the middle, we have a net force down. So this causes our concave meniscus, but as we shrink the radius of the tube, we'll see that a higher proportion of the particles will be dominated by the adhesive force, which means that there will be a greater net force up than down. As our volume increases though, so as we slowly pull that level up higher and higher, then we have more and more fluid that's in the tube, which means the center of mass includes a greater and greater amount of mass, which will increase the weight, and eventually we get to a point where that net adhesive force up reaches equilibrium with the net weight down of the entire tube, and that's why the substance stops rising at a certain level. Before we move on to fluid handling systems, we have to consider a third state of matter. So just like liquid had a special definition compared to fluid, gases will also have a special definition. In the previous example, we saw that all of the tubes were open to the atmosphere. What about closed vessels? In order to understand how this works on closed vessels, we need to understand a specific part of Boyle's law. So gases do not have the same restrictions as fluids, gases are compressible. So this means that our pressure and our volume are inversely proportional. In a closed container, if you shrink the volume, the pressure increases. And this is referring to the volume of the container and the pressure the gas exerts on it. Boyle's law also tells us that the pressure and volume need to remain constant. So if we increase the pressure from our initial stage to our final stage, we'll have to decrease the volume. Let's look at a plunger. If we take a plunger that has one set pressure for a volume, and then we push down on the plunger, the volume of the container decreases, but the pressure in the cylinder will increase. So pressure 2 will be greater than pressure 1 here. Syringes and pipettes take advantage of this through aspiration. If we take a pipette and we place the tip underneath a fluid, this is effectively making the container a closed container. When we pull the plunger up, we're increasing the volume of the pipette, which decreases the air pressure in the pipette. With the reduced air pressure, the forces on the fluid outside of the pipette try to push the fluid into the pipette until all the pressures stabilize. This has the effect of drawing fluid up into the pipette. Now, even when we lift the pipette out of the fluid, the surface tension of the fluid and the air pressure outside of the pipette work to keep the fluid in the device for most fluids. We've come to the end of the lecture. It's time to recap what we spoke about today. In this lecture, we explored new concepts related to the interactions of fluids, liquids, and gases, and we considered the difference between each of those three substances. We introduced concepts to examine how these substances relate to physical interactions. This means we looked at the forces that are internal and external to fluids. Those are the cohesion and adhesion forces. As well, we looked at laws and principles that are used to describe the phenomena we see in fluids. This was Boyle's law, Pascal's law, and Archimedes' principle. Eventually, we applied all of our knowledge to better understand the dynamics of fluid handling systems, looking at a tool like a pipette.